In last lecture, we have discussed about the prime numbers and this fundamental theory of arithmetic is very important topic. And here we are revising this page again. Primes are important because they form the fundamental building blocks of all the positive integers. Any positive integer n can be written as a product of primes, like n equals p1 into p2 into p3 dot 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 up to pm equals, this is the product symbol of all the primes starting from p1 k equals 1 up to m pk, where p1 is less than equal to p2 less than equal to p3 less than equal to p4 up to dot 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 less than equal to pm. And this expansion is unique. There is only one way to write n as a product of primes in non-decreasing order. Here it should be in non-decreasing order, like p1 less than equal to p2 less than equal to p3 and so on. This is known as the fundamental theorem of arithmetic. There are an infinite number of primes. We know that. Euclid's proof assume that there are a finite number of primes. Call the list of primes p1 p2 p3 up to dot dot pk, where k is the number of primes. Define the number n, the product of all the primes, plus 1, like if n equals p1 into p2 into p3 dot dot pk plus 1. Consider the smallest divisor of n, d, greater than 1. D must be prime because if it had divisor, they would also divide n, but none of the primes in our finite list, this is second point and this is very important, but none of the primes in our finite list it a divisor of n. If you divide n by any of those primes, you will always get a remainder of 1. Same, so d is a prime not in our list. This is a contradiction, so there must be an infinite number of primes. So here we can simply give the explanation for the infinite number of primes. Euclid was the greatest mathematician between the 325 BC to 265 BC. Now the nth prime Pn is about n times the natural logarithm of n, like Pn is n log base n, n log n. This allows us to estimate the density of primes within a range of integral values. There are 25 primes between 0 and 100, so the density of prime is 1 in 4. For 10 digit numbers, the density of primes is only 1 in 23. For 100 digit numbers, the density is 1 in 230. The density of primes is inversely proportional to their length in digits. Generating small prime numbers. One simple way to calculating prime is used to sieve off